Okay. So, so since this transition rule is probabilistic, even if you started the system in a definite state, say all the spins were up initially, since the transition rule involves a probability, that means that in the future, every given state will occur with some probability. So if you have some kind of time evolution, so if you have some kind of time evolution, then the probability, so you go through the system in some steps. Let me do it like this, okay? So remember that this alpha labels the state of the system. And this n here labels one of these steps. So you started with some initial configuration, and then you step through the 1, 2, 3, 4, 5, 6. So even if the initial state was a definite state, you can only specify a probability that you will encounter a given final state after n steps. So this is the number of steps. And this rho is a probability. Okay, it's the probability of this state alpha. Okay. So, so the way this whole thing then works is that this Markovian time evolution will just take a probability of a configuration that you started with. Again, the initial one could actually be definite, so that there's only one state and it occurs with probability 1. But as you step through it, you will just get probabilities. So you have a kind of Markov time evolution. Oops. And so what that does is you want to know what is the probability of a state beta occurring in step n plus 1. And what that is given by is you have all the possible states that occurred before, and then there is a transition probability. So the sum alpha is over all possible states of the system, and then there's a transition probability that you go from alpha to beta, and there's wherever you were before. Okay, so that's the rule for updating these probabilities. Okay, and so there's some simple constraints here. Number one, again, these p beta alphas, they're probabilities, so they must be positive. And they must be less than 1. Okay. They must also be, as usual, probability must be conserved. So the sum over all possible probabilities must be 1. So if I sum over all possible final states of the system for a given initial state, that must be 1. So alpha is some kind of initial state, and then you have a transition rule that initial state goes to some final state, but the initial state doesn't just disappear. So the sum of all probabilities that, alpha could be all spins up, and then beta are all possible states of the system. So conservation of probability means that you end up somewhere, okay? So this is normalized. And note that these probabilities need not be symmetric. So it's not the case that P beta alpha is the same as P alpha beta. And the reason that we don't really expect that to be symmetric is because what we would like to do, what we would like this algorithm like Metropolis to do, is explore, the partition function of the system. But the partition function of the system, what it really corresponds to is ultimately thermal equilibrium. So we would like it to be the case that if you start out the system in some configuration that's far from equilibrium, that it tends towards equilibrium. But that must mean that these transition rates cannot really be symmetric. It cannot be equally likely to go from a really ordered state to a disordered state and to go the reverse direction. That way it would never really equilibrate, okay? So in general, we don't expect these to be symmetric. So as I mentioned, what we would like these algorithms to do is to equilibrate. Okay, what we mean by equilibration is that you start out the system somewhere, and it shouldn't matter where you started out. So you started out in step one with some probability distribution over all possible states. As I say, that doesn't even have to be a real probability. It could just be that one state has probability 1 and all other states have probability 0. But now we update with some kind of probabilistic rules, so now we get genuine probabilities. So we update to row of 2 and so on. And so what we would like is that the system eventually equilibrates. In equilibrium, the states themselves may still change, that spins flip up and down, but the probability that certain spins are up and down, that should no longer change. That's what we mean by equilibrium. So what we want is that we eventually get to some magic distribution rho star that's now stable in time, so that once you reach this equilibrium distribution, it doesn't change anymore, okay? So a distribution like this, where's the inequality? So, so this one here, that was an inequality. So these probabilities can be numbers between 0 and 1, including 1. You can go to one particular state with certainty, in principle.
Dr. Schäfer, I meant the probability going from alpha to beta, is it equal to the going from alpha to beta?
Oh, sorry. Yes, I made a mistake there. So I did say need not be symmetric, and then I wrote an equal sign. Okay, very good. So I meant this to be an inequality, sorry, a not equality. Okay. Yeah, so what we would like the system to do is to equilibrate. And so this rho star, that would then be an equilibrium distribution. Okay. So formally, this equilibrium distribution satisfies, that P beta alpha, when acting on this rho star, gives me the rho star back. Okay. Or if I suppress indices, okay, I would simply write that P acting on rho star, my transition rule just gives me the distribution back. Okay. And so if you want to be a little more mathematical, this P, after all, is some kind of matrix, and this distribution is some kind of vector. So this equilibrium distribution is an eigenvector of the transition rule. So it's a right eigenvector. And since the transition rule is not symmetric, you can distinguish left and right eigenvectors. So this rho star is a right eigenvector of the transition rule with eigenvalue 1. So rho star is a right eigenvector of P. with eigenvalue 1. Okay. So this is what we mean by equilibration. Okay. Another concept that we need is something called ergodicity. So ergodicity we've already previously encountered in sort of standard mechanical systems. So here, what we mean by ergodic is simply the fact that somehow the state space does not fall apart into little islands, so that you can always get from any given state to any other state. So we have some transition rule. It could in principle be the case that you have some large state space. So this is a sort of abstract space. Again, it's really 2 to the n dimensional. And what we want to avoid is that somehow falls apart into islands. Okay, so this is what we don't want. So if that was the case, then if you start out the system in one of these islands, you could never reach, if the true equilibrium distribution is in some other island, then you would never be able to reach it. So, so ergodicity is simply the fact that you can reach any state from any other state. So by ergodic here, we simply mean that we can reach every beta from any alpha. Okay. And finally, another magic condition that we have to impose on these Markov chains to do what we want them to do is to satisfy something called detailed balance. And we will go through these and see how the Metropolis algorithm satisfies. So right now, this seems a little abstract, but we will go through this and see how the Metropolis algorithm satisfies all of this. So what we mean by detailed balance is that we get to this magic equilibrium distribution, and we already saw that the equilibrium distribution is stable under our rule. So we saw that P alpha beta rho beta star, okay, if summed over all beta, so I suppress this kind of sum in that case, that gives me the distribution back. Okay. So this was just the equilibrium condition. But there's another condition which sort of applies without the sum. So imagine you look at the same expression, but you don't sum over beta. Okay, so you're in equilibrium and you're asking, what is the probability to have some state, up, up, down, down, go to some other states where, instead of up, up, down, down, it's whatever, up, down, up, down. There's surely some probability. Even in equilibrium, you'll still get fluctuations. However, ultimately, these fluctuations cannot change the equilibrium distribution. So what must be the case is if you have 2 given states, then the transition from 1 to 2 must be the same as the transition rate from 2 to 1, because otherwise you would start to shift the equilibrium distribution. So it must be true that this is the same as the reverse. Okay. And this is called detailed balance. So you know, somehow the way this is sometimes drawn, like if you imagine you have a quantum mechanical system with a bunch of states, that this Markov chain, it has some transition probability. So this is some state alpha, this is some state beta. So we have some transition rate this way, we have some transition rate reversed. If you don't want to change the occupation numbers of these two levels because you're in equilibrium, then these two transition rates must be the same. So that's called detailed balance, that as soon as you get to equilibrium, these two rates are now the same. Okay. So as I said, I don't want to do mathematics, but I do want to state the sort of master theorem, which is, you know, under what conditions does one of these Markov chain algorithms do what we want it to do? So what we wanted to do is to somehow, as you step through that Markov chain, we wanted to sample a thermal equilibrium distribution. So if we take some physical observable, like the magnetization or the energy of the system, and we sample it during this evolution, that what we're really sampling is a partition sum, okay? We want to know under what conditions that works. Okay, so the magic theorem is the following. So we have, you know, what's referred to in the book as a discrete dynamical system, but for us, a discrete dynamical system is just some kind of state space plus a transition rule. So there's a discrete dynamical system, okay? So this thing, you know, what that means is simply there's a state space plus a rule, some kind of transition rule. Okay, so a system like this, it converges to an equilibrium state if the following things are true. Number one, so this transition rule P is Markovian, so it only depends on the current state of the system. So that was this condition of no memory. The transition rule is ergodic, so at least in principle, it can take you from anywhere in state space to any other place in state space, and it satisfies detailed balance. Okay. So that's the magic theorem. Any algorithm, and I claim Metropolis is just an example of this. So any algorithm that you can find that satisfies these three conditions. So you have a Markov process. So you just have a rule that takes you from one state to some other state. It's ergodic, so your rule is somehow rich enough that it can take you in some finite number of steps from any place in state space to any other place. And it satisfies this detailed balance condition. So whenever that happens, it will drive you to some kind of equilibrium condition. And the kind of equilibrium condition is simply the one that refers to this detailed balance condition. There is, by the way, if you formulate it like this, there is one place where it looks a little circular because we defined the condition of detailed balance with reference to some equilibrium distribution. So if you somehow look at this as a theorem, it looks like this is sort of circular, that in order to define what you mean by detailed balance, you already need an equilibrium distribution. And so there's a sneaky way to get around that, which is you can define detailed balance. There's an equivalent definition of detailed balance that doesn't refer to some rho star already existing. So let me just briefly mention that sort of for completeness. So detailed balance can be defined as follows. where you never use the fact that an equilibrium distribution exists. So the trick is the following. The trick is that instead of 2 states, you can consider 3 states. So imagine you have 3 states, alpha, beta, and gamma. Okay. So now you can define transition rates between the 3 of them going around in a circle. So for example, you can go from alpha to beta, beta to gamma, gamma to alpha, or you can do it the other way around. Okay. So again, you have alpha, beta, and gamma. So you can go the other way around, which means you could go from alpha to gamma, then you go from gamma to beta, and then you go from beta to alpha. And the statement of detailed balance can simply be defined as the statement that these two are the same. So if you want to write it out as a formula, what that would be is that P of alpha to beta times P of beta to gamma times P of gamma to alpha is the same as going the other way around. Okay. And I think the book actually offers this as a little exercise. It's not that hard to see that if there is an equilibrium distribution, this condition is actually the same as the previous one. But the beauty of this definition is it makes no reference to an equilibrium distribution. So formally, it can be checked without knowing that one exists. Okay. So, so this is a little abstract, but it's actually somewhat useful. It's useful in the following context. So again, we have this Metropolis algorithm, which works beautifully and it can be applied to many, many systems. But sometimes people, for various reasons, tweak it because they think that for their particular system, they'd like to use a slightly different rule. Now, you want to make sure that whatever changes to the rules you make don't destroy the fact that you're sampling an equilibrium distribution. So you would like to know, what it is that you have to check. If you're trying to run some kind of probabilistic algorithm that's supposed to sample a statistical distribution, you want to make sure that it's actually guaranteed to sample the right thing. So what this theorem provides you with is just a bunch of conditions that you can easily check. And so let me show you how we check it for the Metropolis algorithm. Okay. So again, our example is Metropolis. Okay. So number one, this thing is Markovian. So the Metropolis algorithm, it updates the spins, but it only depends on, the current configuration of the spins. You don't need to know anything else. So that's kind of trivially true. Okay. It's also ergodic, and that too is kind of trivially true because the Metropolis algorithm, it just flips single spins. Okay. And you can reach any configuration of spins by just one after the other flipping single spins. Okay. So that can certainly be done. So the algorithm is kind of trivially ergodic as well. So the one thing you have to check is that it satisfies detailed balance. So that's the thing that requires a little more effort. Okay. So so what we're supposed to check, we're supposed to check that P alpha beta of rho beta star is the same as the other way around. Okay, again, remember there's no sum. Okay, so really what we can check is the ratio of these two transition rates. And what this says is that P alpha beta divided by P beta alpha must be rho alpha star divided by rho beta star. Okay. So, so you can in principle check this by this magic triangle rule, and then you don't have to know what rho star is. But here we already know what it is that we wish to simulate. So here we wish to simulate an equilibrium distribution, which is at the Boltzmann distribution. So here we actually already have a candidate for what it is that we want to get. So we want to get that rho alpha star, this equilibrium distribution, has some overall normalization, which is the partition function. So let's just write proportional. So we want this to be proportional to e to the minus e alpha over k Boltzmann t. Okay. So then what we would like to check is that the ratio of these two transition rates is just the ratio of these exponentials. So we want that P alpha beta divided by P beta alpha is, so P alpha beta is proportional to rho alpha star. So we want this to be e to the minus e alpha minus e beta over k Boltzmann t. Okay. And so obviously this is some kind of energy difference. Okay. So we want to make sure that the ratio of the transition rates is just exponential in delta E. Okay. So, and okay, now you can already see why the Metropolis algorithm was constructed in the way that it was, because that's indeed this probability that was used in the construction of the Metropolis algorithm, that the probabilities are somewhat proportional to e to the minus delta E. Okay. To see this explicitly, so in the Metropolis algorithm, after all, there were sort of two rules, one that applied if you lower the energy, and another one that applied if you increase the energy in your spin flip. So, so for definiteness, let's consider one of these possibilities. So one of the two states, alpha and beta, is the one with the lower energy. And so for simplicity, okay, I'll just pick one. So I picked the one that beta is the one with lower energy. And so then this delta E is a positive number. Okay. So, so now what was my rule? Okay, so somehow now it would be better if I'd written this on a different whiteboard. So let me just write it down again. So what did I just write down? I wrote down that P alpha beta divided by P beta alpha is e to the minus delta. And delta E was defined as E alpha minus E beta. And again, my assumption now was that E beta was less than E alpha. Okay. So then how did the Metropolis algorithm work? So P alpha beta over P beta alpha. So if beta is less than, if E beta is less than E alpha, then if I have a transition that goes into the lower energy state, I always accept, okay? So the probability to do that was 1. We always accept that move. And the other transition from beta into alpha, since now I'm going up in energy, I only accepted that with probability e to the minus delta E over k Boltzmann t. That was the rule. But again, what we were supposed to check is that indeed this ratio is e to the minus delta E. Okay, and so that's obviously the case. So this one finally gets a check mark too. So, so we conclude from the whole exercise that this metropolis algorithm, it satisfies detailed balance, and it sort of trivially satisfies this Markov property and the ergodic property. So then this theorem guarantees that an equilibrium distribution exists. We actually already kind of know what it is. It's just a Boltzmann distribution. But it also guarantees that the probability will indeed just approach this Boltzmann distribution. Okay. So once we know that, now we really do know that we can use the metropolis algorithm in kind of the way we want to. So we can now measure things that, we have this kind of process, and we can, for example, compute the average magnetization by just following this Markov chain. Oops. So I'm following this Markov chain. I make, some number of steps. And in every step, I just measure what the magnetization is. Okay. So this is magnetization in some configuration. Okay. And on the left, this is now my average. But it's the average corresponding to the distribution rho star. But this rho star, we know from checking the detailed balance condition, is just the Boltzmann distribution. Okay. So we know that this metropolis algorithm kind of does what we want it to do. So it eventually just samples a Boltzmann distribution. So computing the average magnetization from a bunch of samples is ultimately the same thing as computing it from the partition function. So this metropolis algorithm therefore samples the partition function, okay? So, so as a homework exercise, I actually assigned that that you try to do this yourself, that you try to write a little algorithm where you run the metropolis algorithm for the Ising model. And so I think that should be pretty straightforward. I also provided a few hints, and the textbook has a few hints, but I wanted to make just a few notes as to what one has to be kind of mindful of in general. Okay. Okay. And there's sort of three issues. One is that if you actually, like the statistical mechanics model that you have in mind, maybe some, macroscopic number of spins, 10 to the 23 or something like this. And so roughly speaking, what we have in mind is an infinitely big system with, infinitely many spins. But of course, on the computer, you never simulate infinitely many spins. You just simulate some finite number of spins. So we always somehow have to take the thermodynamic limit of either taking the volume to infinity or for taking the number of spins to infinity. And that can actually be a slightly subtle issue for the following reason. So again, what we ultimately expect to see is something like this, for example, that if you run your algorithm at different temperatures, okay, and you measure the average magnetization, what we mentioned earlier is that we think that the Ising model has a phase transition. So we think that if you do this as a function of temperature, you get something like this that actually has a sharp phase transition. Okay. But this is supposed to correspond to some average that's taken with regard to this partition function of the Ising model. But the partition function so Z is, a sum over all possible states. Okay. So if you have a finite number of states, this sum is just a sum of a finite number of exponentials. And if you now compute the average magnetization by, say, taking a derivative with respect to an external field, if you take a derivative of a bunch of exponentials, it's still a bunch of exponentials. So the partition function for a finite system and all observables, which are derivatives of the partition function, is just a sum of exponentials, finitely many exponentials. And now a finite number of just ordinary exponentials is a perfectly smooth function, for any number. If you have 7,371 exponentials, and you sum them all up, it's still a perfectly smooth function. So any finite sum like this can never have a sharp transition like the one I drew here. So for any finite number, this transition cannot be sharp. It has to be smooth. So in a finite volume, or for a finite number of particles, okay, the actual transition can never look sharp. And all you can see, or all you can try to study, is that if you make the number n bigger, or if you make the volume bigger, then it must look more and more discontinuous. But any finite simulation will never look discontinuous. Every finite simulation will always look smooth. Okay. So the best you can hope for is that if you make n bigger, then, okay, somehow starts to look sharper, but it's never going to be infinitely sharp. So this is a bigger value of n. Okay, and then the green curve would correspond to infinite n. Okay. And so in practice, that presents some kind of difficulty if you want to use a Markov chain algorithm, like the Metropolis algorithm, to precisely locate this TC, the critical temperature here. Okay, so this point is the magic TC. So if you want to use a numerical algorithm to locate this TC, then the difficulty is that for any finite n, and that's the only thing you can ever simulate, there will not actually be a sharp discontinuity. So you will only see some kind of crossover, and the crossover just gets sharper and sharper as a function of n. So that actually means you have to do a certain amount of numerical work, because you somehow have to see how this scales as a function of n, so that you can somehow extrapolate to infinite n and see where that discontinuity occurs. Okay. So, and it's of course in general true that, even if you're not at TC, at finite n, whatever magnetization you measure is just an approximation to the exact value as n goes to infinity. But as long as you stay away from TC, this kind of extrapolation is easier, because at least everything is perfectly smooth. Whereas near TC, you have a bunch of curves, every one of which is perfectly continuous, but they're trying to approximate a discontinuous function. So that's somehow a more complicated extrapolation. Okay. So that's one issue, that you have to somehow look how this extrapolates to infinite n. And in practice, you somehow have to figure out which n is big enough. It's always possible that your n was too small and there's some crucial feature that you're missing. Okay, that's one issue. The other issue is the issue of initial conditions. Okay, so when you run a Markov chain algorithm like Metropolis, then you measure some quantity like the magnetization as a function of these steps. Okay, so they're Monte Carlo steps, or sometimes called its Monte Carlo time. It's not real time, it's just the time that elapses as your algorithm runs. And so you measure some quantity, like you measure the magnetization in every one of these configurations, okay? And what that will do is it'll somehow fluctuate eventually around some kind of equilibrium value, okay? But presumably you didn't initialize it to that equilibrium value. For example, you could have initialized your configuration so that half the spins are up and half the spins are down. Then you actually started down here. So then if you let the algorithm run, what it will somehow do is somehow fluctuate. And the idea is that eventually it fluctuates around the equilibrium, okay? Something like this. But you could have alternatively, of course, started from somewhere else. You could have started in a fully magnetized configuration where all the spins are up, okay? So then you start somewhere up here. Now, the theorem says that the thing will converge. So this should ultimately reach the same equilibrium configuration. So this should look something like this, that initially it fluctuates somewhat differently, but eventually it fluctuates around the same mean value, okay? And so this is then actually a kind of a neat check, because if you're unsure, you know, again, initially your system is not in equilibrium. What the theorem just guarantees is that eventually it'll get there, but it doesn't tell you how long that eventually is. And so this dependence on the initial condition, it's some criterion that you can use in order to see how close you are. So at least if you start from two different initial states and your magnetization has converged to the same final state, then that's some guarantee. It's not an absolute guarantee, but it's some evidence that your algorithm has indeed converged, okay? So this here is effectively some kind of estimate of an equilibration time. Okay. So this is dependence on initial condition. And finally, one more thing we need to consider sometimes is dependence on boundary conditions. This is my difficulty of writing at the top of this board. Come on. Okay, that's just not right at the top. Okay, so the issue is the following. As I say, maybe in principle, we're interested in an infinitely large system of spins, but in practice, of course, we can only do finitely many. So in practice, we have some kind of lattice and say, okay, this could be an extremely small lattice. So this one has only 9 spins in it. Okay, so then the issue with this lattice is the following, that the standard Metropolis algorithm, you know, you update a spin, and for the update, you needed to know the values of the spins of the neighbors. Okay, so you have a spin in the middle, which is the one we're updating, and then what you had to check was, you know, the 4 neighboring spins. Okay, but you see that this lattice here is so small, there's only one spin that actually has 4 neighbors, and then there's a whole bunch that have 3 neighbors, and then there's the ones on the corner that actually have only 2 neighbors. And so, so the question is how to best deal with spins that sit on edges. And there's various ways to do that. I mean, like one simple rule would simply be to just, you know, use the rule in the way it's written, that I only have to check the neighbors. And if a spin sits on an edge, then, well, it has fewer neighbors. And that's perfectly fine. I mean, that will play less and less of a role as the system gets bigger and bigger. But there is a rule that often helps in minimizing the effects due to the fact that, you know, your lattice is not as large as you want it to be. And the standard trick is to use periodic boundary conditions. So what periodic boundary conditions means is that you sort of imagine that this lattice actually wraps around. So that if you're considering a spin that sits on one of these edges, say you have a spin that sits here, okay? So now we can still assign 4 neighbors to it. We can say there's one neighbor here, there's one neighbor here, there's one neighbor here, and the 4th neighbor sits here, but of course there's no point on the lattice, but we just wrap it around periodically. So we just say that this one is equal to this, okay? So this is a periodic lattice where effectively we're applying periodic boundary conditions. Okay, and so effectively what that kind of means is that, and I'm not going to be able to draw this well, is that your lattice actually lives on some kind of torus, okay, where if you run out of the lattice on the right, you actually come back on the left, okay? So that's the kind of geometry that on our lattice that effectively we can go around in the circle this way, or we can go around in the circle this way. So if we have our lattice, and what these rules effectively are, is if you exit the lattice on the right, you come back on the left. Or if you exit the lattice on the bottom, you come back at the top. Okay. That's sort of one extra line of code in your computer, but with arrays, this is easily implemented. And this periodic boundary condition usually has the advantage of minimizing finite size effects, because this way you ensure that in some sense there's nothing special about the spins on the edges and the corners, because they still have the same number of neighbors. Usually, if you imply some kind of boundary condition that effectively there's nothing to the left and the only neighbors to the right, then now there's something special about the spins on the boundary. And so it tends to be the case that this minimizes the finite size effect, although there's never a guarantee, I think. So I'll just say it tends to minimize. Okay. So so just what that might look like, I was going to quickly show you. So I wrote a little easing simulator for myself, which I can briefly share with you. So where is it? Oh, here it is. Okay. So this one was written in Mathematica, which is actually incredibly inefficient, but never mind. This is not meant to be professional, but in Mathematica, you can make very nice plots. Again, in the homework assignment, I don't necessarily ask you to make fancy plots. So, so what you see here is some kind of lattice. I think it's 50 by 50. And instead of plotting up and down, I plot yellow and blue. Or, within the code, of course, there's not up and down. There's just -1 and +1. So, so this, by the way, here there's already a place where you can see that I have 2 different ways of initializing the system, which I call hot and cold. And so obviously what cold means is that all the spins point in the same direction. So I offer 2 different ways of cold. So the cold can simply mean all spins up or all spins down. So this M is either plus or -1. And the other one is a hot lattice. So the reason that there's a seed is simply because the random number generator has a seed. but then the actual spins are just random integers between -1 and +1, okay? So then you need this kind of rule for updating them. In principle, the rule for updating them is very simple. All you have to compute is the change in energy. And so for every spin, you just have to find the 4 neighbors. And the one complication is, again, you somehow need a rule that has some kind of prescription. The only complication here is really there's some kind of prescription as to what exactly happens at the boundary. And here, indeed, I wrote a rule that kind of periodically wraps around. And so there's a special condition so it's a 2-dimensional ladder, so it's labeled by 2 integers I and j. And so the points I equals 1 and I equals the size of the system, or the point j equals 1, or j equals the size of the system, these points are special because those are the points where you have to wrap around, okay? So I have a little function that just evaluates the change in energy, and the only thing that it needs to take care of is what exactly happens to spins at the boundary. And then I have to compute the magnetization. So I imagine that I have an array of spins that are just plus or minus 1. And the total magnetization is just the sum over all of these spins, okay? And so now I can write a little Metropolis algorithm. And so all the Metropolis algorithm has to do is it goes through all the spins, and for every spin, it tries to calculate the change in energy when you flip. And then you have to incorporate this actual Metropolis rule that so if the energy is less, then we always update. And if the energy is not less, then we update with some probability, okay? And somewhere down here, I actually turned this into a little movie. So this is maybe the one thing we can try to execute. So I think this will take just a second before this movie starts to run. Okay, here we go. So now this is just a movie of running a bunch of updates. You can actually see that apparently I started with something that's totally random. So the initial configuration is really a very random set of spins. So let me stop it somewhere. So you see that initially, this was just truly random. So I just picked every single spin randomly. But then I let it run. And of course, you know, the interaction is such that neighboring spins have some preference for being parallel. So even if the system is not globally magnetized, there is still some preference for some local domains to form. And you can see that in the simulation, that as you let it run, it apparently wants to have not necessarily the whole system magnetized, but at least it wants to have domains of a certain size. And exactly how big these domains are, that will of course depend on the temperature, okay? The other thing that you can do is that, so this is now one of these plots where, you know, so on the x-axis, it's indeed just a bunch of configurations. So apparently here I made 500 lattices of 50 by 50 spins, and I let it run as a function of time, and I just monitored the magnetization. And you can actually already see that it's a little bit hard to say in general whether the system is magnetized. So this probably is in some regime where on average it's not magnetized. But of course, over a certain period of time during the simulation, you know, here on average, the magnetization is positive. Then it makes an excursion where on average it wants to be negative. Here's again, it wants to be on average positive. So probably this is a regime where on net, the magnetization is at least pretty small, because again, the mean magnetization per spin, it could be as large as 1. And here it seems to kind of fluctuate between -0.3 and +0.3. But then you can do many, many runs like this and do that for different temperatures, and you get some kind of curve. So this is now, this axis is temperature, and this axis is magnetization. And so now you indeed do see that at very, very low temperature, the magnetization is pretty close to 1. But as you go to higher and higher temperature, it starts to drop. Again, here you never encounter a sharp transition. This is this thing that I mentioned previously. For any finite number of spins, it will never be exactly sharp, but you should see that as you make the number of the size of the lattice bigger, it should start to sharpen up. So I think this here is an example of that I do two different simulations with different size lattices, and it starts to look a little bit sharper, but it's still not perfectly sharp, okay? So again, this actually requires a certain amount of experimentation to see how this works. Okie dokie. So this is just how my thing looks like. Again, your thing can certainly look different than that. Okay, so let me go back to my whiteboard. Oh no, did I lose my whiteboard? Huh. Okay. Okay, I guess I learned one more thing about this whiteboard, that if I ever leave it, it just disappears. Okay. In any event, so okay, so this is basically all I wanted to say about Markov chain Monte Carlo and about the Metropolis algorithm. And again, I think the best way to learn the whole business is just to try to do it yourself, and then you see what all the difficulties and the pitfalls are. Okay, are there any questions about this? Okie dokie. So then I wanted to continue with a sort of new thing still related to easing, which is just more generally. Again, the easing is just an example of an algorithm that's trying to simulate a magnet and study a possible phase transition in a magnet. So, so you can view the easing model, again, as an example of a more general class of questions as to what kind of phases of matter there are and what kind of phase transitions can occur. So I wanted to talk about this more generally, is I wanted to talk about something called order parameters. And as we'll see, that's related to broken symmetries. So this whole chapter of the book, or this whole section of the course, what it really is about possible states of matter. And possible phase transitions. Okay. So, so first of all, what do we mean by a state of matter? We'll make it more precise as we go along. Maybe for now, I just give a bunch of examples. Okay, one example that in some ways we already encountered is, magnetism is a kind of state of matter. So, and there are different kinds. So there's standard magnetism, which is usually called ferromagnetism. So you have a state of matter that's being magnetized, and there seems to be a sharp transition, which is this Curie temperature from going from non-magnetized to magnetized. And that has a cousin, which is called an antiferromagnet. Antiferromagnetism is what happens in the Ising model if you make this coupling negative, so that neighboring spins don't want to be parallel, they want to be anti-parallel. And you might think that you somehow cannot tell, because then the magnetization, after all, is always zero. So then the magnetization is either zero because the spins are totally random, or it's 0 because now, next to nearest neighbors are always up and down. So that actually always locally averages out. But there are ways of telling. Number one, antiferromagnetism actually is a real thermodynamic phase transition. So for example, if you take an antiferromagnet and you measure a specific heat, you do see a sharp discontinuity at the Curie temperature of an antiferromagnet. And you can also still tell by doing magnetic measurements. So effectively what this means is that you shouldn't look for magnetization that's spatially homogeneous. You should look for magnetization that varies on a given length scale, which is roughly the lattice spacing of your lattice. So if you can somehow test the system with magnetic fields that have a spatial resolution, then you can tell whether the system is antiferromagnetically magnetized or not. That, by the way, is sometimes called a staggered magnetization, because really the system is still magnetized. It just so happens that the magnetization flips on every alternating lattice side. Okay, so that's one kind of state of matter. Another state of matter that you may have heard of is superconductors or superfluids. That's secretly, as already kind of indicated, post-condensation. And again, all of these are actually sharp thermodynamic phase transitions. So if you measure something like the specific heat, there's a sharp discontinuity. There is, in some sense, what is actually historically kind of the most obvious example, but where the details are actually slightly more complicated sometimes, which is, this just kind of classical transition between solids, just systems with crystalline order, and various disordered phases of matter, things like liquids or gases or plasmas. Okay. So the thing that's more complicated here, and at some point we will learn why that is that, so the transition from a solid to a liquid or a gas or a plasma is always a sharp phase transition. But we already saw when I drew this phase diagram for just ordinary water that the liquid gas phase transition sometimes is sharp and sometimes it isn't. And the liquid plasma transition, again, sometimes sharp and sometimes it isn't. The gas plasma transition, by the way, is never sharp. So that's always just a smooth crossover. And at some point, we wish to understand why that is. Okay. And in condensed matter systems, there's actually infinitely many other examples of this kind of type of stuff. Like for sort of soft matter people, liquid crystals are very rich set of examples, various polymer melts and God knows what, all sorts of interesting phase transitions. And then there's new classes of systems, which sadly we don't really cover in this course, that are actually not quite in the paradigm that I'm about to discuss. These are things like quantum Hall states. And nowadays, there's also things called fractional quantum Hall states. Okay, so there are many, many examples for states of matter that we would like to understand. So we'd like to understand why they're different in the first place and why you sometimes see this as thermodynamic phase transition. So you actually see something discontinuous happening in something like a specific heat. Okay, and one of the claims is that the fact that something sharp happens is related to symmetries and broken symmetries. And I will try to make that a little more precise eventually, but for now, I'll just mostly draw pictures. Okay, so so let's again go to magnet, and I'll consider something for reasons that we'll discuss, which is a slight generalization of this Ising magnet, sometimes called the Heisenberg magnet. And a Heisenberg magnet is simply a continuous version of Ising. So Ising was every spin is either plus or minus one. Heisenberg is just a spin that's an ordinary vector in space. So on every lattice side, you just have a spin s, and it's not plus or minus 1, but it has, say, a fixed length. Okay, that's a possibility. So, so if you have a lattice of these kind of Heisenberg magnets, so what that would look like. So, so I have some kind of volume. Okay, and you have a lattice. Okay. So then again, the system could either be magnetized or it could be non-magnetized. So non-magnetized would simply mean that, so these are now real vectors, but they point in effectively random directions. Something like this. This would be a non-magnetized state, and what a magnetized state would look like is simply you have the same system. So here's my lattice. And now my spins are all oriented in some direction. Okay. So this would be unmagnetized. And this would be magnetized. Okay. So what does that have to do with symmetry? What it has to do with symmetry is that once the system has a definite magnetization, as in the second case here, so the magnetization is now some vector and it's not zero. Now, this vector has to have a definite direction now. In the picture that I drew it's all up. And so one way to say this is to say that rotational invariance is now broken because there is a preferred direction in my system. Okay. Whereas over here, so the average magnetization is 0. Oops. Okay, which means there is no preferred direction in the system and rotational invariance is respected. Okay. Now, it's still true, of course, that if you zoom in on any given neighborhood, the spins are pointing in some direction, So in any small neighborhood, the spins are pointing in some direction, but no neighborhood is somehow special. On average, they all look the same, okay? And the mean magnetization is just 0, so there's no preferred direction in the system. So one way to think about this kind of phase transition where the system goes from non-magnetized to being magnetized is you can think of it as a transition where the symmetry of the system changes from being rotationally invariant to being not rotationally invariant, okay? And so I will give more examples of that on Wednesday. And so I hope that this will become clearer. In the meantime, you can also start to read, again, the book has a whole chapter about broken symmetries and order parameters where a lot of these examples are discussed.